In this video, we will do a proof using mods. All right, so let's get right into an example, into a proof. I'm gonna let n be an integer, and I wanna prove that n squared is either congruent to 0 mod 4, or n squared is congruent to 1 mod 4. So, okay, let's get a feel for why this is true by looking at some examples. So if I think about what n squared could be, and then on the side, I'll keep track of, well, what would n squared mod 4 be? Remember, n squared mod 4 means what's the remainder when I divide it by 4? Well, okay, so if I did 0 squared, that's 0. 1 squared is 1. Then I'd have 4, 9, 16, 25, and so on. Those are my perfect squares. If I divide them all by 4, well, 0 divided by 4, it goes in evenly. That's just 0. There's no remainder. If I did 1 divided by 4, the remainder is 1. 4 divided by 4, the remainder is 0. 9 divided by 4, well, remember, 9 is 4 times 2. 4 goes in 2 times, and then plus 1. So the remainder is 1 there. 16 is a multiple of 4, so no remainder. 25 will have a remainder of 1, and if we try even more values, all the remainders will always either be 0 or 1. So this is interesting because, you know, when I think about remainders when I divide by 4, remainders in general could also be 2 or 3. But somehow when I square my integer, the only remainders I'm getting are just 0 and 1. All right, so let's prove this. Okay, so I'm going to start off my proof by saying what it is that I'm given, that n is an integer. And then seeing that I'm trying to say something about mod 4, let's look at n mod 4. Let's look at n in mod 4. Okay. Because when I do that, there's 4 possibilities for what the remainder could be. So this gives us 4 cases. The first case is, well, n could be congruent to 0 mod 4. That means that n, when I divide it by 4, it'll have a remainder of 0. Okay, that's the first possibility. So if that was true, you know, we've seen before that when we have a congruence like this, that we're allowed to raise both sides to a positive exponent power. So this means if I square both sides, I'll get n squared is congruent to 0 squared. That was one of our theorems, mod 4. Mod 4. Well, and 0 squared, well, that's just 0. So I get 0 mod 4. Okay, so in the first case, I'm getting that n squared is congruent to 0 mod 4. And that's one of the things that is acceptable. Okay, so case 1 is working. All right, the next case is, well, what if n is congruent to 1 mod 4? The next case would be n could be congruent to 2 mod 4. And the last case is it could be congruent to 3 mod 4. Okay. And what this is going to do for us is, you know, instead of having to check, you know, an infinite number of values and make sure it works for all of them, well, it lets us just group them into these 4 cases, and that'll show that it's true for all of them. So because if n is congruent to 1 mod 4, if I do the same thing and I square both sides, we'll get n squared is congruent to 1 squared. And now I'm going to do a bit of a shorthand. So instead of writing this kind of line by line like I did here, it's really common when we use congruences to just keep doing congruences, simplify it as much as I can, and then at the end of it, write the mod. So if I get 1 squared, that's congruent to just 1, and that's the simplest it can go, and I have mod 4. Okay, well, that's the second possibility. It's congruent to 1. That's good as well. All right, what about case 3? What if n is congruent to 2 mod 4? Well, squaring both sides, I'd get n squared is congruent to 2 squared. And 2 squared is 4, right? 2 squared is 4. But 4 is congruent to 0 in mod 4. That's the remainder when I divide 4 by 4. Okay, so that gives us this possibility, which is totally fine. One more case. What if n was congruent to 3 mod 4? Well, squaring both sides, I get n squared is congruent to 3 squared. 3 squared is 9. And then what is 9 congruent to mod 4? Well, 1. It's got a remainder of 1 when I divide by 4. Okay, well, that's the second possibility, which is also okay. So therefore, what we've shown is no matter in which of these cases we're in, n squared will always end up being congruent either to 0 or to 1 in mod 4. And that's what I wanted to prove. Okay. All right, so that's our example of a mod proof. So one of the reasons why this is so nice is up until this point, back in chapter 1, when we did casework like this, the casework was a lot more tedious. We were doing things like, well, what if n was odd? Like n could be 2k plus 1. And what if n was even and n is 2k? And we'd be taking stuff like that, and then, I might be squaring it and doing algebra. And, I could do it, but it was just longer and more tedious. And using mods drastically speeds up that process. Okay, all right, let's do part B of this example. So here's an application of why a result like this might be relevant. That the only possible remainders when you divide a perfect square by 4 are either 0 or 1. Why that might be relevant. So the problem says prove there are no integer solutions to a squared plus b squared being equal to 4,567. Okay, so I want to show that there's no positive integer solutions to that equation. So when we're trying to do this, we could try to do what's called brute force. We could try to use brute force and, look at all the combinations of squares that I could plug into this that might be okay, that are, less than or equal to 4, 5, 6, 7. Because if they were bigger than that, there's no way it's going to equal 4, 5, 6, 7 on the other side. So I could try to, consider all of them, but that's going to take us a long time. That's going to take us too long. I'd love to have a more efficient way. Okay, so here's a strategy tip. We've seen this before, that often when we're trying to show that there's no something, that can be difficult to do directly. And that's often a tip-off to try a proof by contradiction. Right, we saw that a number of times back in, going back to chapter 1 now. So with the proof by contradiction, we assume our conclusion is false, and then show this leads to a contradiction, something impossible happening. Okay, all right. So let us see what this looks like. So in this proof, I am going to, because I deliberately put it kind of underneath this, I'm going to be using mod 4s, and then we'll see in a sec why that's so great. I'm going to use mod 4. And I'm going to assume for the sake of contradiction, assume for the sake of contradiction that there do exist an a and b, which are integers, such that a squared plus b squared equals 4,567. One of the ways I know to use mod 4, besides the fact that I'm doing this right below a problem in which I used mod 4, is that, in this problem I have these perfect squares. And one of the things I know, based on what I proved above, is, well, perfect squares have a very limited number of remainders, mod 4. Either the remainder is 0 or 1. So maybe when I add them together, maybe the remainder of this side won't match the remainder of the other side. Because if that happened, well, that's an impossibility. That would be a contradiction. Okay, so indeed, that's what we're going to try to get. So now what I'm going to do is, we know that if I look at the left-hand side, we know that either a squared or b squared, so comma b squared, both of those are either congruent to 0 or to 1 in mod 4. Which implies that when we add them together, that a squared plus b squared, their sum, I'm going to be adding either zeros or ones or a combination of the two. So when I add those, either it could be 0, if I get 0 plus 0, or it could be 1, or it could be 2. So I'd get this if I had 0 plus 0. I'd get 1 if I had 0 plus 1, or 1 plus 0. And I'd get 2 if I had 1 plus 1, if both of these were congruent to 1. Okay, so a squared plus b squared is congruent to either 0, 1, or 2 in mod 4. Okay, so I'm really hoping that 4, 5, 6, 7 will be congruent to something else. Because if it is, we get a contradiction. All right, so let's check that. However, if I look at 4,567, well, what is that congruent to in mod 4? So we might recall, going back to elementary or middle school, that when you divide something by 4, ultimately, all you got to do is check the last 2 digits. Ultimately, you just got to check the last 2 digits. So this ends up having the same remainder as 67. One of the ways I can see that is, I know 4 divides 100 evenly. Divides 100 evenly. So it'll divide any multiple of 100. So it'll also divide 4,500. And if it divides 4,500, what's left when I find the remainder of this divided by 4 would just be the 67. So this is congruent to 67. And if I divide 67 by 4, well, the remainder is 3. So this is congruent to 3 mod 4. And that is exactly what I was hoping to show. This is a contradiction, because the two sides are congruent to different things. Okay, this is a contradiction because one side is congruent to 3 mod 4. Let's highlight this. Congruent to 3 mod 4. The other side is either congruent to 0, 1, or 2 mod 4. So therefore, remember my symbol for therefore is these 3 dots. Therefore, there are, what did I start off by assuming? I assumed that there are integers that satisfy this equation. That means there are no integers a and b such that a squared plus b squared equals, let's write that b squared better, b squared equals 4,567. And that completes my proof. So let's just quickly recap one of the strategy points about this. So often when we're trying to prove that there's no integer solutions to some equation that involves like powers of variables, a very common technique to tackle that is to find an appropriate mod to analyze that side with. And that's something that we get better at if we study this a bit further and we look at other examples of stuff like this. In our class, we're really just going to scratch the surface. And, if we find that right mod to look at it at, hopefully we can show that the two sides are congruent to different things with that mod. So they have different remainders when divided by the same thing, because that's a contradiction.